Are you good to go at this point?
Yeah, that should be fine.
Okay. I actually have a second laptop computer sitting next to me so that if I have problems on my end, I don't have to reboot my computer. I can go straight over to there. So let's get back and talk about odd and even functions, because that's the only way we can do these problems, is by knowing how to tell if a function is odd or even. Odd functions. The test is always to see what f of minus x is. That is the test on whether you have an odd function or an even function. If it's an odd function, then it's equal to that. Sine is odd. So if I said, what's the sine of minus x? It's the same as minus sine of x. Cosine is even. Excuse me, I need a negative sign right there. The test is always to test negative x. But if it's an even function, f of negative x is equal to f of x. And that would be cosine and sine. Okay? You with me?
Yep.
All right. So how can we tell if this is odd or even? They say it's odd. So this has to be true. Well, let's see. If I substitute minus r for r, I get, what's the numerator?
It's negative.
Negative r to the 15th. What's the denominator?
3 plus cosine squared r.
You will notice that that is the exact negative of that, based on that negative sign. So we know it's an odd function. Not all functions are either odd or even. Most are not, but some of them are odd or even. And when you find one that is odd, then you know, as long as the limits of integration are merely a positive or a negative from one another, then the whole area's got to be 0. So we don't need to do any math. We just need to recognize that that's an odd function, and that's how we're going to solve it. Okay, let's go on. Those are kind of unusual. I don't get too many of those. 12. Any possibility of
This one,
what's that?
this made no sense to me when I was trying to do it.
Well, you haven't had integration by parts yet, correct? Or have you?
I don't think so.
Okay. So the only two techniques you have to integrate at this point are power rule, if it's a polynomial or a trig function, just find the antiderivative, plus U-Substitution. So at this point, you don't need to investigate a whole lot of types of integration. At some point, you will. I'm not sure how far you'll go in calculus, but there's like 10 different types of integration. And the biggest problem becomes when you get a hard integral is to figure out which type method you have to use to solve it. And there's also figuring out whether it's odd or even. I wouldn't even begin to know how to solve that if you hadn't pointed that out. I'd still be working on it. 12, not hard. Why?
It's just a simple U problem, isn't it?
The U-Substitution. Why? because we have a composite function multiplied by the derivative of the inside, or at least the same power of the derivative of the inside. That's what's important. It's not x to the 1/3 or x cubed. It's x. And what's the derivative of the inside?
X.
No.
2x.
2x. But we can handle that too.
Yeah.
That 2 is no problem. So we do have the same power. Okay, so let's go through it. We now know that it's going to work with U-substitution. Okay, so let's do it. Always do it, same method every time. What's U? The biggest
U
problem
is just...
Yeah, it's not really a difficulty figuring out what U is. If we look at all these functions through 14, it'd take us about 2 seconds to figure out what U is in all of them. 13, that thing in the parentheses has got to be U.
Yeah.
Okay.
U is just x squared plus 1.
Okay. Next step. Well, it's always the first step in integration problems most of the time.
Is it du dy?
Yeah, take the derivative. Only it's not du dy. What is it?
Dx dy. Or du dx.
Du dx. Understand what you're taking. You're taking the derivative of the function u with respect to x. Okay, and what is that again?
2x.
Keep going. What's the next step?
And then it's du equals 2x dx.
And the last step. We'll do this one more time this way, and then I'll show you a slightly easier way to shortcut 2 of these. But until you really get it down, I would suggest keep doing it this way.
Is it just du over dx, or du over 2x equals dx?
There you go. In other words, you got to solve for dx, right? Remember always what we're going to do here is we're going to turn this integral into an integral of u. So let's start writing it. All right here. So it's now what? Write everything you can. Well, x is still x.
Yeah.
This thing is now u. Keep going. Give me the rest of it.
And then 1/3, or raise to the 1/3. And then it's du over 2x.
Which is magical because now that x gets rid of that x. And now you have an integral of u to the 1/3 over 2 du. Now I can either take that 2 out as a 1/2, or I can just leave it there. I don't need to take it out. Now, there's a catch here. My limits of integration for my u integral are not the same as they were for my x integral. Okay? 2 ways to handle it. Personally, I kind of like doing the integration, and then switching back to an answer in x, and then evaluate it at your original limits, minus √7 to 0. So let's try that. So first of all, integrate that.
It's just x squared plus 1, all in parentheses, to the 1/3.
We have an integral in u, integrated as an integral in u. One step at a time. Always start by adding 1 to the exponent,
Oh, okay. So it's 4/3, or yeah, 4/3 to 2,
Now what?
and then
You
3/4.
You divide by the new exponent, which is the same as multiplying by its reciprocal.
Yeah.
So there is our integral. Now I'm not going to put the c on it because we're not going to need the c. Now the next step is to resubstitute. So I've got 3/8. U is x squared plus 1 to the 4/3. And I can now evaluate that at the same limits, minus √7 to 0, as we're on the original integral. In other words, I convert it to an integral in U so I can integrate it. Then I resubstitute and give my answer as an answer in x, and then I evaluate it in x at the new limits of integration. Okay? And this looks like it.
Yep.
This looks like it might be hard, but it's not going to be that hard. You know how to do that, correct?
Yeah.
You always start with the top number, substitute it, come up with an answer, subtract out the bottom number, substitute it. Do we need to go through that?
Yeah. Nah, I think I got it. It was just getting to that step.
Well, hold on. Let's back up a moment. I want to make sure you see the other way you can do it. I'm not sure I've ever seen a time where you have to do it this other way. You can almost always do it relatively easy. I have seen some calculus problems, though, that act like you might have to sometimes do it this other way. So if I want to evaluate this while it's in U, I can do so. But I got to go figure out what these new limits are. In other words, what is U when x is 0? Up here on the upper right. Tell me what U is when x is 0.
1.
Okay, so that's the upper limit of integration. Tell me what U is when x is negative square root of 7.
Is that just -6?
Well,
Yeah, -6.
Plug in, you got to do this. Negative square root of 7 squared plus 1. Well, this becomes 7. Plus 1 is 8. Okay.
Oh, yeah, I messed up the sign.
Okay. So now we do have a little bit of a problem here. We're going from a bigger number to a smaller number, which never happens in most integrations. And I'm not quite sure, to be honest with you, how we handle that problem. We could probably just answer it and put a negative sign on our answer and we'd be correct. In other words, I believe that this function evaluated from 8 to 1 is the same as negative this function evaluated from 1 to 8.
I think that's what my teacher said that it is.
But notice that we don't need to do it this way, ever. We can always resubstitute the x's back in for U and then evaluate it at the original limits of integration.
Okay.
Okay, let's go on to the next one. Well, hold on. Before we do that, I want to show you something else, as long as we're dealing with a nice, easy one here. Notice that when we get to this step right here. And what I always do is have you solve for dx, right? Because after all, we've got to substitute for that dx. Well, there's a slightly different technique that is used and usable, and that is, can I find that anywhere? Oh, I can. There's the x, there's the dx. So all I need to do is find a 2x dx, and I can do that substitution without going there. Well, how do I do that? Well, let's put a 2 there and a 1/2 there. That's the way they teach it. In other words, I'm looking exactly for a 2x dx, and now I've got it. Okay? So,
Yep.
I can, wherever I see 2x times dx, I can substitute du immediately. So what do I have? I have 1/2. The 2x dx is du, and the x squared plus 1 is u to the 1/3. So I can get to that step a little bit faster. I don't actually need to go from here to there and then cancel the x's out. In other words, when you do the problem like this, I've had high schools act like that's not even U-substitution. That is just using the power rule. But in fact, it is U-substitution. And in fact, that was probably just a student that misunderstood that this is not U-substitution when we do it this way. This is the way most schools teach it, right here, is when you get to that point there, then you start looking at your function to see if you have any x dx's next to one another. And they're not always next to one another, but they just need to be there. Or specifically a 2x dx. Now, this little trick where you add the 2 and then take a 1/2 out there, notice is all I did is that's 1, right? That's like multiplying by 2 and dividing by 2, only putting the dividing part outside the integral. You can always take numbers outside the integral, or put numbers inside the integral if you want, which is what we did in this case. So let's try doing the next few this new way. Do you know which way you were taught? I mean, I'm not sure. I want to do it the way they taught it to you. Which way?
The second way.
Okay, good. And I think the only reason I worry about making sure a person knows how to do it the first way is because then you're just doing it one step at a time and you're just substituting everything. Okay. What am I looking at down here? Wow.
This one I had no idea where to start.
I can see why. I'm not sure I know where to start. Let me think about it for a second. Let's see. The derivative of tangent is secant squared. So, and it's on the opposite side of the fraction bar, which you usually don't want. So I'm not sure that's the way to go. And the derivative of that is 3t squared, and there's a t squared there. So, think for a moment. This might be a double U substitution. Trying to think of why that's in the bottom. Let's start by making U. Let's see if we get anywhere by doing this. Making U T cubed. Ooh, hold on a minute. Have you had U substitution by change of variable yet?
No.
I bet you have. I bet they just didn't focus on it. Let me give you an example. I can't solve that. Well, at least you don't know how to solve it yet. Okay? But if I let U equal x plus 1, and now what's du dx? Well, that's just 1. So du equals dx. And by changing the variable, I turn it into something. If u equals x plus 1, what does x equal? X equals u minus 1. So what I have is excuse me, I meant this to be x over x plus 1. That's the one I can't solve. And notice what happens. This is not the pattern recognition form of U substitution. And as far as I know, there's really only 2 methods for doing U substitution. There's the kind we've been doing, where you have a composite function multiplied by the derivative of the inside of the composite function. And then there's change of variable, like this. Notice what happens when I do this way. I end up in the top, x is u minus 1. In the bottom, x plus 1 is u. And du is dx. So now I can do that one. Why can I do that one? Because I can break that fraction up. In other words, I can break it up into u over u minus the integral of 1 over u. And I know how to do that integration, and I know how to do that integration. What I don't know how to do is that integration without using change of variable U substitution. You with me?
Yep.
Okay. So that's another method of U substitution that's not quite the same. This step right here is a little different. You have to actually, their first step is to solve for x in terms of u. Actually, the first step is to still take the derivative of it, but once you find that the derivative is 1, now you have to also solve for x in terms of u. So, a little different technique there. All right, I wanted to make sure you knew about that. Whether it's applicable here or not, I don't know. We got a lot of strange things going on with this function. I'm beginning to see what might work. Yeah. Okay. I'm going to let u equal t cubed minus 1. Now, this is definitely not change of variable yet. So, what's the rest of it?
That is...
What's the next step? Now that I've identified what I want to make u.
Find the antiderivative of it.
No? Remember, the first step in these integration problems is almost always to differentiate. It's going to be the first step when you go to integration by parts. It's the first step. Just get used to it. the first thing you need to do is identify u and then take the derivative of it. So what is it? du what? Du d what?
dt.
Okay. That's equal to that, which means we're going to end up with a t squared next to dt. And that's a good thing. I can see where we can use that right now. So we're looking for t squared times dt. Well, here's a t squared. There's a dt. So I can immediately substitute du for that. So let's see where that takes us. I'm not sure that's going to help that much, to be honest. I think I've maybe got to do something with this -1 first, but nonetheless, let's have a look. So the t squared and the dt, actually I'm looking for a 3t squared dt, so let's put a 3 there, which means we have to put a 1/3 there. Now I do have a 3t squared dt, which I'm going to substitute du. Now I still have my secant squared of t cubed to deal with, but down here I've got tangent of u.
Squared, right?
Ah, yes, squared. Tangent squared of u. Okay, what does that give us? That gives us, let's write it in a slightly better way, secant squared of t cubed times tangent minus 2 of u du.
Did you forget the 1/3 off the front of it?
I did. Thank you. That, however, is not my problem. Or is it? In other words, can I solve this integral? Yes. If I now look at my inside, no, the inside is now tangent of u. Let's go over here and make up a new u. Let's call it v. So v equals tangent of u, correct?
Yeah.
So this is going to end up looking like v to the -2. And what's dv? du equals secant squared of u. So dv equals secant squared of u du. So now I can turn this integral possibly into an integral in v. Just a second repetition of using U-substitution. Because I'm kind of looking at that, am I not? There is my secant squared. There is only one problem. What I made u? I made u t cubed minus 1. I maybe want to make u just t cubed, not t cubed minus 1. Question is, boy, they made this doubly tough.
Yeah, if you made that, If you made u t cubed minus 1, wouldn't you have to make v tan u minus 1?
Well, except,
Or can you not do that?
now hold on, you might be onto something here. In other words, if I made u t cubed minus 1, so that's t cubed minus 1, that's secant of t cubed minus 1. We're not looking at that. We're looking at secant of t cubed. So I don't think I can make u equal t cubed minus 1. Hold on, let me think about this 2 more seconds. Maybe I can, though. No, I can't. No, because the derivative of tan is secant squared of u, but u is t cubed minus 1, and we're not looking at that. We're looking at secant squared of t cubed. So somehow I got to get everything in terms of t cubed. Let's start from the beginning here. I thought that that was going to be a problem all along. So I want u to be t cubed, not t cubed minus 1. Now, oh, this would have been such a simple problem had they left off that minus 1. Would have unfolded perfectly as a 2-step U-substitution problem. Let me think just a moment. That would make this tan of u minus 1 squared, which if I do expand it, it becomes tan squared of u minus 2 tan u plus 1. Now I've got 3 terms in the denominator. That's not helpful. I guess what I'm going to recommend, I don't want to waste any more time on problems that I can't do.
Okay.
If we're going to have another session, I will definitely look at this and see if I can figure out how to solve it. But for now, I suggest we go on, merely because 14 I do know how to solve. How do I know I know how to solve? First of all, why does U-substitution, why is it going to work here? What is U going to be?
U is going to be sine to the 4th.
No.
No.
Here's the difference. Let's go back and talk about differentiation. If I differentiate that, what is the inside? Over here on the left.
If you differentiate that, wouldn't it just be?
The inside, if you had to make up a U, now they don't always use U-substitution when they're talking chain rule, but there is one situation that confuses most of my students, and that's the difference between these two. U is different. In this case, U is sine of x, because that would make this U cubed. In this case down here, U is x cubed, and that makes that sine of U. Notice the difference. I can integrate that, or I can differentiate that rather, and I can differentiate U cubed.
Okay.
Okay? In other words, And listen, let me not pass this because this is really important. So differentiate this for me. Remember what it is. It's u cubed. Differentiate it. How would you differentiate u cubed?
It'd just be. Oh, okay.
U squared, right?
Yeah.
Okay, well, u is sine x. So if you're differentiating that, it's 3 sine squared of x, but I got to apply the chain rule. What's the derivative of the u? Remember,
The derivative, it's, yeah.
there's the derivative of the u, cosine x. So whenever you see something like that, recognize that pattern. Cosine x is the derivative of the inside of that composite function. Sine squared x is a composite function. Sine x is the u, and it's u squared. When I take the derivative of this, well, here I got to let u equal x cubed, and now I'm taking the derivative of sine u, which is cosine u, so it's cosine, completely different, times the derivative of the inside, which is 3x squared. So distinguishing between these two examples, sine cubed of x and sine of x cubed, is extremely important whether you're talking differentiation or integration, because I need to be able to recognize that pattern. Well, notice that's the pattern we're looking at right there. We've got the composite function, and we've got its derivative. Well, we know what happens when we use U-substitution. That's what we're looking for, is we're looking for the derivative of a composite function to be multiplied by it. So let's go do this one. Top to bottom, tell me what U is, every step. Got just enough time to do this one, I think.
So U would be 3x.
No. Remember what U was when I had sine cubed of x. U was sine x.
Okay, so
it's sine 3x. That's what U is. Now, the next step is always what?
the du dx.
Tell me what that is.
Cosine 3x.
Times. Don't forget to apply the chain rule.
X or 3.
Times 3.
Yeah.
Okay. So now du is 3 cosine of 3x dx. Let's see if we can find that. There's the cosine of 3x dx. The only thing I'm missing is a 3. So let's put a 3 in here. In fact, how about if I take that 15 and turn it into a 3 times a 5? There's my 3. There's my 5. See what I did?
Yep.
Now I'm looking for that, and I see it. There's the 3 part of it. There's the cosine 3x dx part of it. So all I got to do is turn all that into du, and I end up with sine to the 4th of 3x, which is what in terms of u? What is that in terms of u?
To the 4.
What is that in terms of u? Here's what u is.
Yeah.
So what is that? What's sine to the fourth? Is u to the fourth, right?
Yeah.
Okay, that's what it is in terms of u.
Okay.
U to the fourth, and then all that other stuff, the 3, that all became du. Notice how we've turned it into an integral in du. Now I'm going to purposefully leave off the limits of integration. Notice that that is not an even function, that is an odd, that is not an odd function, that is an even function. U to the fourth is an even function. Okay? So I can't just assume it's 0. We're not looking at an even function. Besides that, my limits of integration have changed. Now, let's do it what I consider to be the easy way, which is to go ahead and integrate it as if it were a definite integral, and then we'll evaluate it at the original limits. So when you integrate this, what do you get?
3u to, or
No,
3u
always
to
start
the
with
fourth.
the exponent. Always, whether you're doing differentiation or integration.
So
When
it's
you're
the
doing integration,
third.
start with that exponent, add 1 to it. That's always step 1.
Oh,
And then
wait.
divide
So
by the new exponent.
it's the fifth. And then, so it's,
That's what it is. Okay?
Yep.
2 simple steps. Add 1, divide by the new exponent. That's always what you do with integration. With differentiation, you still start with the exponent, but you multiply it and then subtract 1.
Yep.
Okay, so now let's go back and substitute what we had for u before we try to evaluate this. Because I can't really evaluate this because those aren't my limits of integration when it's u. I can use those limits of integration only after I get it back into that's u to the fifth. Now my function is completely a function of x, so I can evaluate it at my old limits of integration, minus pi over 2 to pi over 2. Again, sine is odd, so we can't assume that's 0. So let's just, for the heck of it, go through this evaluation. You can't forget your trig when you do calculus. Trig is, I mean, you've seen that. You got to know all your trig pretty good. So first evaluate it up there. What's the sine of pi over 2?
It's 1.
Okay. What is the sine? Excuse me. I didn't mean that. I meant I'm substituting pi over 2 for x. So what's the sine of 3 pi over 2? That's what I want. That's minus 1.
Yeah.
Okay. So on top, while we're doing it, let's figure out what I know I'm going to have to substitute this lower one at some point in time. So what's the sine of minus 3 pi over 2?
That is 1.
Correct. Okay. So let's do the evaluation. So we've got the sine of 3 pi over 2, which is minus 1 to the 5th power. That gives you minus 1/5. That's the top thing evaluated. And now we're going to subtract out evaluating it at minus pi over 2. Well, that's plus 1/5. So we have minus 1/5 minus another fifth. There's your answer. That is the area under that curve. And it's net below the x-axis because it's negative.
Okay.
Okay. Now, again, the other technique is to figure out what u is at minus pi over 2 and make this an integral and leave it in u and evaluate it in u. I got to think that for most people, I don't see that as being more efficient. In other words, I see these two steps being identical in the amount of work you have to do. Whether you substitute and evaluate at the old limits of integration, or you figure out what the new limits of integration would be in terms of u and evaluate that at the new limits of integration. You'll still end up with minus 2/5. But this method still requires you to go through and figure out what u is at minus pi over 2 and what u is at pi over 2. So you still have to do the same amount of work. I don't see it being any easier at all, because all it is a little bit confusing. Like I said, I think I found one problem in a calculus book that made sense to do it, to evaluate it at the new limits of integration. But even that one, you could still figure it out by doing it the way I'm doing it here. All right. Mitch, I'm sorry we didn't get further. And I'm sorry about 13. I got to give 13 some thought. But depending on when your next session is, I'll have 13 done by today, by the end of today. So if you need a way to do 13, I'll be working on it today. I'll be ready by tomorrow morning if you want to do something like that.
My test is tomorrow morning, so can you?
Okay, so this is.
Yeah, but that's really, I've done the rest of them.
Okay.
Like the rest of all this stuff, and a lot of them I can get pretty easy. It was just these 4.
Those 4? Okay,
So,
good.
can you email me your way of doing 13?
I can probably, yeah, I probably can. Once I figure out how to do it, I'm pretty sure the solution lies in what to make u. I just got to figure out what to make u. I don't know whether I want to make it t cubed or t cubed minus 1. I can't seem to figure out how to handle it when I make it t cubed minus 1. Oh, you know what? You can't make u t cubed minus 1. Notice that. This is the tangent of t cubed minus the quantity 1. It is not the tangent of the quantity t cubed minus 1. So it was stupid to even make t cubed minus 1 be u. That doesn't, you don't have the tangent of u. T cubed minus 1 is not the argument of the tangent function there. T cubed.
Yeah.
So we've got to let t cubed be u. I'll bet that actually solves the problem. I think. I don't know. I'll have to do it. I'll let you know. Okay. The email may just be as simple as let u be t cubed. I don't know. I'll give it some thought.
Okay.
All right.
Thank you.
Mitch, talk to you later. Good luck on your test.
All right. Thank you.
Bye-bye.
Bye.